So an important, very, very important thing to be able to calculate for ionic species are formula weights. So a formula weight is the mass or how much one unit of an ionic species weighs. Okay, so remember what ionic species are. They're something with a metal, generally with a metal and a non-metal. It's two ions coming together to form some sort of ionic compound. And the way to calculate these is by adding up all the sums, so the sum of all the atomic weights for the atoms in the chemical formula. Now, if you don't recall what the atomic weights are, let me show you just for. So, for an ionic compound, such as calcium chloride, sodium chloride, or something like that, what you're doing is you're adding up all the atomic weights for those particular atoms. So you would add up one atomic weight of calcium, two atomic weights of chlorine, one atomic weight of sodium, two atomic weights of chlorine. Okay, so if we were to use an example here, so what is the formula weight for calcium chloride shown right here? We would go to the periodic table. Here it is. We see that calcium is right here. It's got an atomic weight of 40.078, and that chlorine's got an atomic weight of 35.453. Now remember that the units on this would be atomic mass units. So scooting back to our table, so we would say, cutting down a few sig figs, there's one calcium, 40.1 AMU, plus two calciums, 35.5 AMU. But there are two of them, so we multiply that by 2, add that together, and we see that we get a formula weight for calcium chloride of 111.1 AMU. That's how much one of those ionic compounds, one single species, one ionic compound weighs, is 111.1 AMU. Now there's almost an identical kind of idea for molecular weight, for molecules as there are for ionic compounds. The only difference is we change what we call this weight. We now call it the molecular weight. So this is the sum of all atomic weights, AW, of the atoms in a molecule. So for a molecular compound, remember there's something that is covalently bonded. You're just adding up all of the weights for the atoms, the atomic weights for atoms found on the periodic table. So if we consider ethane, for instance, we have 2 carbons, 6 hydrogens, and I've got it right here, but I want to show you where I got this information. Again, going back to the periodic table, right underneath the element symbol, we see the atomic weight. So hydrogen looks like this is 1.00794. I'm only keeping two sig figs here though, so only going to one decimal place. And then carbon, 12.0. So 12.0, it says 12.0107, but I'm just going to again keep one decimal place. So 2 times 12.0 plus 6 times 1.0 equals 30 AMU. So that's the molecular weight for ethane. Finally, one other thing we might want to know is how much or what percentage by mass of a particular compound or what percentage of an element is for a particular compound. So it's the percent by mass that is contributed by one element type. Okay, so the way you calculate that is you put the number of atoms of that particular type times the atomic weight for that element. Okay, so and then you multiply it by 100. Don't realize that this is just to change it to a percentage. There should be a percentage sign right there, and then you divide that by the formula weight or the molecular weight for the compound. And so, for example, if we have ethane, we've already discussed that the molecular weight for ethane on the last slide was 30.0 AMU. If we want to find out how much carbon is in the ethane, we would start plugging in numbers. We have 2 carbon atoms in the formula, say 2 and 2. The atomic weight for carbon is 12.0 to one decimal place. And then we would divide by the molecular weight for that particular formula, and then multiply it by 100 to change it to a percentage. So this is how to actually calculate percent composition. Now you might ask, why in the world would you want to do this? Why would you want to know what percentage of a particular substance is oxygen or gold or something like that? Well, gold's pretty obvious if you want to know what percentage of a compound is gold. But but one of the reasons that this is done all the time for us in forensic research, if somebody discovers a white powder, well, it's well known that certain illicit drugs have a certain percentage of carbon. Okay, say that cocaine, for instance, might be 82% carbon. Well, they can actually calculate, they can run these through certain mass analyzers. They're basically calculating what percentage of a particular substance is carbon. If they find out that that substance matches that of cocaine, let's say, like I said, cocaine is something like 82%, and if they find out that their white powder has a percent carbon of 82%, that's one more indication that the white powder is an illicit substance. And so that's the type of reason why you would want to actually calculate the percent composition for an element in a particular species.